Hello and welcome to this video on light. Specifically today we're going to be talking about the Doppler effect in light and how it applies to astronomy. A common thing to look at in chemistry classes are these emission spectra. These are what happen when an atom or an element gets energized. They start emitting lights at specific wavelengths. Specifically, hydrogen will emit this red band, the cyan band, blue, and the various shade of purple. And each element will have their own distinct set of colors. And they only ever come in those colors. Every hydrogen we look at has this emission spectrum. Every helium we look at has this emission spectrum. Neon, sodium, and so on. And it always comes in these colors of light. The problem came when we started looking at other stars. When we looked at certain stars, we started noticing that we get the same pattern as hydrogen, but they'd be in slightly different spots. They'd be offset. And the pattern is still the same, they're just shifted higher up into a redder section. This caused a small amount of confusion. What could cause this? What was going on? And then they thought of the Doppler effect. The Doppler effect says a moving object producing a wave, such as light, will change the frequency. Well, if the frequency is changing, so must the wavelength. In each of these cases, the frequency went down, so the wavelength had to go up. We refer to this as a redshift. When lines shift towards the redder end of the spectrum, their wavelength is increasing. Now, this small amount of shift is notable, but it also means that there's other changes going on. All these are producing different frequencies as well. This happens because the source of the light is moving away from us. The waves are farther spaced out. The crests are farther apart. If we talk about the duck, go back to the duck that we looked at previously and compare it to the star, if we look over here, the wavelength is higher because the duck's moving away. The same is true of the star. The wavelength goes up, the frequency goes down. Whenever we see a planet emitting light from elements that is red shifted, we know it's moving away from us. If we flip the script and talk about a blue shift, something where the lines have moved down, shifted towards blue, they have a shorter wavelength and a higher frequency. Again, to bring it back to the duck, we're on this end, where the waves are more clumped together. In this case, it moves the object, the planet, the star, is moving towards us. Based on how much it's shifted by, we can tell exactly how fast it's moving away from us, which gives us very useful information about where it is in the galaxy and the relative motion of it compared to us. In fact, by measuring differences in the red and blue shift, we can talk about how fast something's orbiting. The math of this is a little beyond the scope of this class, but this is one of the ways that using the property of waves in terms of light can be directly relevant to understanding the world around us. But just how fast does something have to be moving in order to be redshifted? Well, let's go back to this drawing for a second. We said the differences here were relatively small, about 7 nanometers, which means if this is 434, this is 441, which means that the wavelength it was emitted at, 434 nanometers, and the wavelength it was received at was 441. If we're talking about this one, 410.1 would become 417.1. Let's use these two numbers right here and do some calculations. The frequency that corresponds to 410.1 nanometers, F times lambda equals C, or 410.1 nanometers equals 3 times 10 to the 8th meters times frequency. We do need these to be in the same unit, so instead of 410 nanometers, we'd have 4.101 times 10 to the negative 7th meters. If I solve for F, I get 7.315 times 10 to the 14th hertz. Go ahead and find the frequency that corresponds to this 417. If you did the math carefully, you should get these values, 4.171 times 10 to the negative 7th meters instead of nanometers, which gives me a frequency of 7.193 times 10 to the 14th hertz. Very large numbers, with a notable difference between them. I can then take this and put into the Doppler equation. F prime equals V plus minus VO, V minus plus Vs F naught. And because this is light, we can make some substitutions. And we'll make the simplifying assumption that the Earth is standing still. Not strictly true, but from our point of view, useful enough. So I can go, well, the frequency I'm perceiving, 7.193 times 10 to the 14th, will equal C plus 0 over C. And we know it's heading away from us, so we can use the plus sign. How do we know it's moving away from us? Because it's redshifted, because the wavelengths are getting longer. Vs time 7.315 times 10 to the 14th. From here, I can do some algebra, simplify this down. I can divide the 7.315 to the other side, and anything plus 0 is still the same number, so I end up getting 9.9832 equals C over C plus S. And then cross multiply here to get C equals 0.9832 C plus Vs. If I distribute, you'll notice I'm leaving C in terms of C for now. It makes my math a little easier personally, and I don't have to deal with exponents all over the place. Subtract the 0.9832C to the other side to get 0.01678 times C equals 0.9832 Vs. Or if I solve for Vs, I should get 0.017069 C, which means that it has to be moving about 512,0702.283 meters per second. 5 million plus meters per second. It has to be moving a notable percentage at the speed of light. Numbers beyond what we've dealt with thus far. But that's how we can use this to calculate things. Because once we know how fast it's moving away from us, we can start estimating how far away it is from us. Using our kinematics equations, we can start estimating other things about it, such as viability for future life, or possibility of intelligent contact, communication. Anyways, thanks for watching. Have a good one.